of the questions in
Sto
the end.
iniziando. Sì, è
So,
meglio, cioè se mi passi dietro te vedono.
so that beautiful language behind is not too far from here. I remember Fausto when I first was joining with the festival, so it's a few years back, and I have to say I'm very happy to have him again. I remember him as a very entertaining speaker. So let's see. Fausto is well known in his work in fluids, astrophysics, and dynamo problems. I was also quite amazed to see that there's a Fausto Cattaneo that's also extremely well known, even a rock star in drug busting, and he busted the cartels of drugs in Mexico. So congratulations for having time to do all of that. So with that, please, Fausto, you may proceed.
Thank you so much. Anyway, so good morning and good afternoon and good evening and good night to everybody. I am so happy to have the opportunity to give this talk and to be back at the festival, even if it's just in virtual form. We all missed each other so much and for so long, and so I want to thank the organizer for giving me this opportunity. It's like spring. It's like coming back to life after a long winter. So today I would like to talk about constraining the history of the Earth through consideration of its magnetic field, which is a very long title for a rather sort of simple idea. And so I would like to begin by acknowledging that this work was done with David, all of you know, and will be giving a presentation later this week. And I want to start by pointing out two things. First of all, the actual drug buster unfortunately passed away a few months ago, so obviously I was not that Fausto Cattaneo. Although I must say, throughout my life, I occasionally used to think one of these days some guy from Colombia is going to shoot me because they think I'm the other guy. So I always made a point of saying I'm the other Fausto Cattaneo, the one that does not go around busting drug cartels. But anyway, okay. So the other thing I would like to point out from the very outset is that this is not my usual talk. Our usual talk are about things that we have done, and this one is about things that we haven't done, but things that maybe we should do, or maybe someone else will do, and we think they ought to be done, and they may even be fun if we did them. So give me some latitude, and I'll try to explain what I mean. Okay, so the premise of this talk is that there's something about the geodynamo that is kind of funny in the sense that it's peculiar. And it's peculiar in a way that, amazingly enough, it may help us understand how the moon was formed. And it seems funny that something to do with the core of the Earth should end up telling you something about the moon. But hopefully during the course of this talk, that will become, if not obvious, at least reasonable or not crazy. And so this is what this talk is about, is to show that a peculiar property of the geodynamo may actually help us, constrain these theories of formation of the Earth-Moon system. So the way I've organized the talk is that, first of all, I will say a few words about the formation of the Earth-Moon system, and I will introduce a few models. And there are many more than the ones I'm going to introduce. It's just that it's just examples of what these models look like. And I shall say a few words about what constraints we currently have available to discriminate between these various models. And the conclusion of that part will be that maybe we don't have enough constraints to nail down one of these models above all the others. Then I will switch and I will go over to the Earth's dynamo and try to explain why, in this particular context, the geodynamo is peculiar. And so I'll say a few words about rotating convection and these two ideas of back and Mach balance. I'll explain what they are. Some of you, if you're geophysicists, are incredibly familiar with them and probably know a lot more about them than I do. And then I will continue to say that this idea that there are two possible balances, back and Mach, leads to the conclusion that the Earth dynamo is horribly, horribly subcritical. And then I will conclude by arguing how this property, this peculiarity of the Earth's geodynamo that is horribly subcritical, in fact, may provide one more constraint that is so constraining that maybe, if we're lucky and we're clever enough to take advantage of it, we may be able to constrain some of these models and eliminate some of them and come up maybe with a unique one. So that's the overall structure of this talk. All right, so the basic idea is that undeniably we have a move. It's over there. We see it every night, most every night. And so where did it come from? And the general agreement is that some very dramatic event took place about 4.5 billion years ago. And that led to the formation of the Earth-Moon system that eventually evolved into what we have today. And most people agree that whatever event was that led to the formation of the Earth-Moon system, it was dramatic. It wasn't like, a slow, gradual unfolding of the formation of this thing. It was like something was going on and then some really cataclysmic event took place that led to the formation of the Earth-Moon system. Within this broad panorama of possibilities, there's a family that is very popular, and it involves many different models, and it's called the giant impact model or theory. And the idea is that about 4.5 billion years ago, some very large object, the size of a planet, basically collided with the proto-Earth, and the material expelled during the impact eventually formed both these, or whatever was left formed the present Earth, and whatever was expelled either formed maybe an accretion disk or directly formed a big lump that became the moon, but the expelled material became the moon. And then following the impact, in the aftermath of the impact, angular momentum was exchanged, things sort of moved to their current orbit and so forth and so on. And maybe they did it quickly and maybe they did it slowly. But the bottom line is that about 4.5 billion after this event, here we are with the Earth where it is and the Earth where it is. And so we have to account for that. And I should point out right away that not all theories of the formation of the Earth-Moon system are giant impact ones. There are other ones, fission theories, accretion theories, and so forth and so on. And my feeling is that the arguments in this talk will apply to all of them. But in order to do this in an hour, instead of covering every single possible scenario, I'm just going to look at a few to give you a flavor of what these things look like. But this is not in any sense or an exhaustive list of everything that is possible or indeed that is being considered. Okay, so we're going to concentrate our talk on the giant impact family. So here's a cartoon of what's going on. And sort of the giant impact family starts with the assumption that there is a planet about the size of Mars, and that is called Theia. I have no idea why it's called Theia, but there it is. So Theia comes along, and it impacts the proto-Earth. So we have a formed proto-Earth. Bear in mind that 4.5 billion years ago is not that, it's shortly after the formation of the planetary system. So it's not that the planetary system was there for a very, very long time and then this happened. It's just it barely been formed. So this planet, of course, it is not unreasonable to assume that when planets were being formed, there were many more planets around, and so collision between planets were more probable than it is now. Thank God for that. Anyway, so the assumption of the giant impact family is that the impactor is about the size of Mars, and it impacts the proto-Earth. Now, after the impact, part or maybe all of the proto Earth is either liquefied or vaporized. Depends on the details. I'll say more about it in a little bit. And of course, also as a result of the impact, part of this liquid or gaseous material is expelled. And so the expelled material then either form an accretion disk or some more complicated object that I'll discuss called a synestia. And in any case, whatever is left behind becomes the Earth, the present Earth, and whatever is expelled sort of recondenses and forms the moon, either from accretion, either from disk accretion or from some other mechanism where it's just kind of a big lump that is sent out there. And then after the impact, the angular momentum evolves, and basically you have 4.5 giga-years for the system to become what it looks like now. And some models, most of them end up with the moon being a lot closer than to the Earth than it is now, and the Earth typically spinning faster than it is now. And so then you have this period in which the moon recedes to its current orbit, and the Earth slows down. And there are different scenarios in which this angular momentum evolution is kind of slow. So it takes basically 4.5 giga-years for things to end up as they are. And there's some in which the angular momentum loss is very rapid. The Earth formed, and then this very rapid loss of angular momentum, and then sort of fades. I'm just saying that to emphasize that there are lots of different possibilities. Okay, so why are there so many different possibilities, given the fact that they all sort of assume that there is an impact? Is because you have a lot of freedom in how you choose your initial parameters. So, okay, so suppose that you were to set up one of these models. So minimally you have an impactor and impactee. So you have the masses of the impactor, the masses of the proto Earth. Then of course you can pick and choose how the spin axis, and if you can pick just about anything you want, because you figure if the impact is sufficiently violent, you may just simply wipe out whatever the spins were before. So you can pick the orientation of the impactor, the orientation of the proto Earth, how rapidly they were spinning, and you're going to see that some theory exploit that by having a very rapidly spinning Earth. We'll see it in a minute. Of course, you have the impact velocity. You can have parabolic trajectories, you can have hyperbolic trajectories, and then you have the impact geometry, where if you think about two spheres, or if you've ever played the pool, you know that where you hit the ball makes a big difference on the outcome. And so you can hit them bang in the middle, you can hit them to the side, you can have glazing impacts, and so you have a lot of freedom in how you organize the point of contact between the two planets. And then, of course, you have the composition of the proto Earth and the composition of the impactor. So you have a very large parameter space in which to start your model, and depending on where you start, you can come out with different outcomes. But the idea is that no matter where you start and what the different outcomes are in the sort of immediate aftermath, after 4.5 billion years, you have to end up with the Earth and the moon. You can't end up with something totally creative that has got nothing to do with either one of those two things. And so to give you an idea of what these different models look like, I've picked up 3 of them. And as I say, there are many more. There are a lot more than just 3, but I picked 3 to give you a sense of the spread. So there's a standard model, hit and run model, which is also called the canonical model. Then there is one family of models called the hit and run models, and you can imagine what that is about. And then there is one that, until David and I started looking into this problem, I never even heard of, called the synestia model. And you will see that they're kind of these two are not that different, but this one is really a radically different approach to the formation history. And okay, So let me start with the standard or canonical hit and run models, and then at the end I'll tell you what is it that distinguishes the one from the other. So both standard or canonical and hit and run assume that the impactor Theia is about the size of Mars. And in terms of incoming velocity, the Theia comes in on a parabolic trajectory. So you can imagine, so it comes in as the escape velocity, basically. So the idea is that this thing is somewhere else. It goes basing of attraction of the proto-Earth and sort of comes in and gets attracted and then hits the Earth on a parabolic trajectory. So it wasn't moving very rapidly at infinity, so to speak. And in these scenarios, the spin of the impactor and the spin of the proto-Earth are moderate. It's whatever suits your means, but it's neither the impactor nor the proto-Earth is spinning really, really rapidly. So both these things are pretty close to spheres. And generically, both the standard and the hit and run assume that the collision is off-centered. So the impactor does not come in and whack the proto-Earth bang in the middle. And depending on exactly how you set this up and various other parameters, some of the crust is liquefied, or actually almost all of the crust, maybe some of the mantle, and depending on how you set it up, you can liquefy more or less of the proto-Earth. And in all cases, there's material ejected, and this material, whether it forms a disk or it just forms one big glob, will then form the moon. And in all of these models, even though the Earth get whacked pretty hard, I mean, you're liquefying all of most of the crust, you don't really destroy the core. You don't sort of, it gets squished and squashed, but you don't really disrupt it. You don't break it in half and send half of it to the moon or anything like that. So let me see if I can activate this movie. Obviously not. For some reason, maybe. Sorry. Let me. Okay, bear with me for a second. This should be an animation to give you some idea of what's going on. Let's get back to this. Much better. Okay, so this is a sort of a canonical impact, except here, let me start it again from the beginning. Okay, so proto-Earth, impactor, Theia, here we go. Impact. The impact sort of liquefies a lot of the crust, possibly some of the mantle. Now, in this particular simulation, you think, okay, we're done. Here's the proto-Earth, here's the proto-moon. And, then this thing is going to move to where it needs. But actually, you will see in a minute that this particular model was not successful. And the little moon is going to fall back to the proto-Earth. So, okay, better luck next time. But it still gives you an idea what the simulation looked like. But the important thing to notice, whether the moon sort of goes off or falls back, is that even though the Earth received a pretty big whack, it didn't get destroyed. Okay, essentially. So here we go. Boom, the moon is at it. So within this family, the difference between the canonical and the hit and run is what happens to the impactor. And as you can imagine, the canonical one, the impactor gets absorbed. So Theia ceases to exist. It hits the Earth, it gets completely absorbed by the Earth, it gets liquefied and goes off and mixes in. And typically these families, the proto-Earth emerges spinning not that fast. Okay, so the typical canonical one, the Earth after the impact is spinning at about 5 hours a day, and then gradually goes to 24 hours, but it's not spinning incredibly fast. In the hit and run families, unfortunately, I couldn't find a hit and run animation. I mean, I could find them, but I couldn't download them. They were all proprietary. So, but you can look them up. If you look at hit and run scenarios on Google or whatever, you can find lots of these things. In those, the impactor actually escapes. So Theia just runs off, hits the Earth, does all this damage. It causes a lot of material to be expelled, but it doesn't get absorbed. So it goes off and lives a full and happy life somewhere else. And typically, the hallmark of a lot of, if not all of them, of the hit and run scenarios is that you end up with a rapidly spinning Earth. And so then you have to find some way of getting rid of all this angular momentum to evolve the system to its current state. Now, you can see that having these two scenarios offers different possibilities, because you think, okay, if the impactor gets absorbed, the stuff that goes off to make the moon may be a mixture of the impactor and the Earth's material. In the hit and run, you can conceive of a possibility that the impactor comes in, liquefies the Earth, leaves, and most of the moon is made up of the Earth. So the sort of the difference between the hit and run and up to getting rid of the angular momentum and everything is that they give you different scenarios of changing the composition of the moon, and that we're going to see in a minute that that's very important. Okay, so the synestia one, and as I say, until David and I started looking into this, I'd never heard of this thing. So synestia is a completely different scenario. It's still a giant impact, but so let me tell you what a synestia is. So the idea is you still have a Mars-sized impactor, Theia, but the impactor doesn't come in on a parabolic trajectory. It comes in on a hyperbolic one. In other words, it's very, very high energy. So Theia was already moving at high velocity at infinity. So it's really coming in fast, 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 fast. And the other ingredient that goes into making a synestia, whoops, stop, is that it assumes that the proto-Earth, so the impactee, is very rapidly rotating. It practically is rotating at the breakup spin. So the synestia is formed by a high angular momentum, high velocity, high energy impact. And so you can see it here, the rotation is so extreme that the proto-Earth is this kind of discoid. It's very, very prolate. And the other assumption in forming a synestia is that the collision is basically bang in the middle. It's a near center collision. And the idea is this: you have so much impact energy that both the impactor and the Earth completely vaporize. They're not liquefied, they're vaporized. They turn into little droplets. And because the proto-Earth, the impactee, was rotating so rapidly, right after the impact and the vaporization, you find yourself with this cloud of gas that satisfies this funny property that some of it is inside this thing called the co-rotation radius, and some of it is outside the co-rotation radius, where the co-rotation radius is defined by saying that the rotational velocity was the same as the orbital velocity. So you have gas that is simply rotating way too fast in this vaporized material that is rotating too fast for the radius it has. It cannot be in orbit at that radius. And so it moves to a much, much, much larger radius. And so basically you divide everything into material inside the co-rotation radius that forms the core, and the material outside the co-rotation radius that puffs up to wherever it needs to be, forms this very, very puffy donut-shaped accretion disk, if you like, except that it's not going to accrete. And it's this puffy disk that is called the synestia. So the synestias consist of a central region, which was the material inside the co-rotation radius, and then this big extended orbiting torus that is the synestia itself. And the idea is that then the core recondenses into the Earth, and the material in the synestia then rains down onto the midplane and forms the proto-moon. And so let me run So this particular movie is by Sarah Stewart, and it's being kind of jazzed up by the Adler Planetarium. So it's not 100% scientific. It's a bit scientific and a bit like to draw attention, but it gives you the idea. So here's the proto-Earth that is this very oblate discoid, and along comes so here comes Thea, and as you can see, everything gets vaporized. There's nothing left, and in the subsequent evolution, all this some of the vapor ends up in the synestia, and some of it will form the core. And it takes a little bit. It takes about a minute. I'll just let it run. And so that's the core, and the synestia is going to be formed by all the stuff here. And towards the end of the movie, you will see it actually form this donut-shaped object. Now, okay, if you think that you like mixing things, this is the ultimate mixer. If you go for one of these things, after one of these events, there's no memory of what anything was doing before. Everything is gone, and things been completely mixed. And okay, here comes the synestium. And so the idea is then that all of the stuff in here will form the moon, and that thing over there will form the Earth. Okay. Now, these are all different scenarios, and as I say, these are not all the possibilities even within the giant impact. And the giant impact is by no means the only scenarios that people use to form the Earth-Moon system. So there's lots. But whatever you believe happened, in the end, you have to get the Earth and the Moon. And so you got all these constraints that you have to satisfy. And so what are they? Well, you have to end up with the Earth being the Earth mass, and of course the Moon being the Moon mass, which is about 1/100 of the Earth's mass. You have to get the masses right. And no matter what you do, the densities are known quite accurately. So the Moon is about 2/3 of the density of the Earth, and you have to get that right. And of course, exactly that the Earth has the day is 24 hours long. And the lunar orbit is about something like 29 days and a half or something like that, and you have to have the Moon is tidally locked after 4.5 billion years. So you have constraints that come from evolution of the angular momentum. And one of the really sort of big constraints, which I'll discuss in a minute, is this business of the isotopic abundances, or rather the isotopic ratios. So what happens is that after the Apollo missions, all these lunar rocks came down to Earth. They were analyzed, and much to everybody's surprise, or maybe people knew about them, figured it out. But the bottom line is that the message is that the Moon rocks are almost identical to the Earth's ones, and in particular, these isotopic abundances are very, very, very close. And some of them are closer than others, but all of them are very, very close to the Earth ones. And that is very constraining for the following reason that I'll try to explain, because that is important. So, so as I'm sure, isotopes have, they're same element, different number of neutrons. So two isotopes have exactly the same chemistry, but slightly different physical properties, because heavier ones weigh more, they have more mass than the light ones. So they have slightly different melting points and boiling points. So for instance, if you take oxygen, oxygen has 3 stable isotopes, 16, 17, and 18. And if you take rocks on Earth, and you measure, the ratio between the 16 to the 17, the 17 to 18, and whatever ratio you want, and you measure them, they tend to be the same. And if you take a rock from the Moon, it has exactly the same ratio. There's some incredibly high precision. And you say, well, so what? The point is that these isotopic ratios depend quite quite a lot of where these rocks were formed in terms of distance from the sun. So if you take two planets that were formed at different distances from the sun, will not have the same isotopic ratios. They will change quite a lot, because you can imagine that as you're forming these rocks, having different freezing and boiling points will cause one to evaporate before the other and go away. So you're going to get rid of all of the light one before you get rid of the heavy one. You're going to end up, so if you're hot, you tend to have a lot more of the heavy one than the light one, and so forth and so on. So isotopic ratios are a signature of where things were formed. So if you have that the moon and the Earth, have the same isotopic ratios, you have to conclude that either the moon was formed entirely from the Earth and none of the impactor, or that the Earth and the impactor had the same material. And so you would say, okay, then the impactor had to have been formed on the same orbit as the Earth, or you had to mix everything very, very carefully, because you have to end up with this similarity. So this one here is a big constraint. Okay. So you have all these different models, you have all these different constraints, and then the bottom line is like, which one do you pick? And what I would like to do is read you, there's this very good review by Eric Hasbog, and it's called Impact Origin of the Moon. And it really is a pleasure to read, and almost everything I know about this stuff, it came from that one various article, but that review is really very, very good. And so towards the end of this review, this is what Eric writes. My concern is different, that several of these scenarios will, with suitable modification, end up satisfying the physical, geochemical, petrological, and dynamical constraints, and that we will thus might never know how the moon was formed. But I take solace that in trying to find out, we will at least establish the very creative nature of the cataclysmic events that made the planets. So that's his conclusion. If you look at it, it seems one of those, we have good news and bad news. The good news that we're going to fund, the bad news we'll never know. And of course, if you want to turn the bad news into good news, you need more constraints. You need, you need to add something else to what you know to get rid of some of these scenarios and nail one of them. And of course, things being as they are up to now, you would say, well, what are we going to do? Go back to the moon and dig up more rocks, or we have to go, what is it? We already know all the angular momentum, we already know the masses, we already know the compositions. What else can we possibly do? And so the rest of this talk is to try to convince you that we already have that constraint, and it has to do with the fact that the Earth has a magnetic field. And so the rest of the talk is to try to convince you that that may be enough, or maybe not, but it will constrain. So this is now, we're getting to the second part of the talk. And okay, so I don't think anybody will dispute that the Earth is a magnetic field. We know that, it's been known since antiquity. Well, maybe not everybody knows that not only the Earth is a magnetic field, but it's had it for a very long time. So there are rocks that show magnetization as way back as 4 billion years. So it's not unreasonable to think that maybe, the Earth was magnetized even at the time of the impact, or maybe the impact caused the Earth to become magnetized. So we have this magnetized Earth now, and we have to account for that. And the property of the Earth's magnetic field is such that, you can argue it cannot be, you can't say the Earth is one big magnet, because we now know that the Curie temperature of the core the temperature of the core is way above the Curie temperature. So you can't have permanent magnetization. Also, you can't say, well, some event put the magnetic field at the time of formation of the proto-Earth, and it's just been decaying and sitting there and slowly dying away. That won't work either, because the ohmic decay time for the Earth is much, much shorter than 4 billion years. So if that's the case, the Earth's magnetic field would have decayed a long time ago. And then, there's evidence for paleomagnetism that the Earth's magnetic field actually reverses. And so sometimes the North Pole is north and sometimes it's south. And in fact, even as we're speaking, apparently the North Pole is moving towards Moscow, and then if it continues, it'll end up somewhere in the South Pole. So we may actually be in the middle of a reversal. But taking all these things together, the inescapable conclusion is that there has to be a mechanism that regenerates constantly the Earth's magnetic field. And the most likely thing is that it's a dynamo that is driven by convection in the liquid outer core. So the Earth has both a solid and a liquid core, and the outer core, the liquid core, is convecting. And so it's natural to assume that that is where the dynamo is being driven. Okay. So what we need to do next is to look at what convection in the liquid core would look like. And I need to consider two possibilities. What would it look like if there were no magnetic field? And what would it look like if there were a strong magnetic field? So let me begin by saying what convection in the liquid core would look like if there were no magnetic field. So we have an unmagnetized Earth that looks more or less like the Earth, or the Earth maybe 2 billion years ago, whatever you want. And so on the left, there is this picture with all these layers and everything. And the one we're interested in is the yellow one labeled outer core. So the outer core is liquid. It's made of iron, a lot of iron, and something else. And the something else is either oxygen or sulfur, or people don't really know. It could be marshmallows. It doesn't matter. The important thing is that whatever it is, it's lighter than iron. It has a lighter component. And because it has a lot of iron, it's a decent electrical conductor. It's not a fantastically good, it's not a great electrical conductor, but it's okay. It will do for government work. The other thing is that the convection in the liquid core is driven both by thermal effects and compositional effects. So the idea of compositional effects is that if you have a mixture, a liquid mixture, and you solidify it, you will not solidify, the solid will not come out in the same ratio, in the same as the two phases, as a sort of heavy and light phase. And for the Earth, what you do when you solidify onto the solid core is that you solidify more iron than the other component. And so you're enriching whatever is left behind in the light phase, and that causes buoyancy forces at the interface between the inner core and the liquid core. And so that drives the convection. And the other thing is that the Earth is rotating, and in units that are sensible, it's rotating really rapidly. And so angular momentum conservation is very important. The Coriolis force is very important. And so the convection gets organized in this, columnar pattern that I've, indicated here in this picture. And, I gave tribute to G.I. Taylor, one of the giants, and these columns are named after him. And the important thing from our point of view is that these columns are very anisotropic. And so, they have a length L0 that is comparable to the thickness of the depth of the liquid core, but they have a width that is, we expect it to be much smaller than the length, which is LH for length horizontal. And so what I'm going to argue in a little bit is that from the point of view of driving a dynamo, the important length scale that will come in is LH and not L0. And so it's important that we know what this length is. All right. But the idea is that this is what convection would look like if there were no magnetic field. Okay, and so the question is, what is this LH parameter? Okay, so it turns out that, oops, sorry. If you look, okay, so this is simplified. This is in Cartesian geometry. It's, assuming that you have like a Boussinesq fluid, but it will do for as I say, it will do for government work. And the important thing is that the momentum equation in a rapidly rotating system consists of all these terms, but because it's rapidly rotating, the ratio of the inertia terms to the Coriolis terms goes like the Rossby number. And so the Rossby number for the Earth, it's very, very small. And you say, how small? Well, okay, you can estimate the Rossby number by saying, what's the characteristic scale of convection? Well, it's about 100 years. So it takes, 100 years for the liquid material in the core to convect once. And yet this thing is rotating, once every 24 hours. So the ratio between these two things, it's a very small number. It's like 10 to the minus 5. So basically, the upshot of all of this is that this term here, the inertia term, is completely negligible. And another way to think of it is you have this very high frequency waves that are engendered by the Coriolis force, that basically, if you have any imbalance in these forces, this term here can balance them automatically, instantaneously, so that this is always equal to that, and this term here just gets out of the way. So in a system like the Earth's core, the fluid move as if it did not have any inertia forces, okay? So notice that this is very different from the other situation in which inertia forces are negligible, which is a low Reynolds number fluid. Here we're talking about a fluid where the Reynolds number is still enormous, but the Coriolis force is even more enormous and takes care of always balancing these terms exactly, or at least as exactly as you want. Okay, so now if you accept that proposition that inertia forces are negligible, the momentum equation in a steady state, or even not in a steady state, it just looks like this. You have these four terms, bearing in mind that the pressure is just there for a ride. It's just there to take to make sure that the fluid remains incompressible, so that div u is equal to 0. But if you don't believe it, it's okay. Just take the curl of this thing, and then you're going to be left with these three terms, the curl of these three terms, and the pressure gets out of the way. So if you want them to balance, you have to have a balance between the viscous stresses. A stands for Archimedean forces, in other words, buoyancy, which here I just wrote in terms of a Rayleigh number and temperature fluctuation. But in really, you need compositional effects as well. And of course, the Coriolis force. And two dimensional numbers have emerged, the Rayleigh number, which is a funny one. It's a rotational Rayleigh number, and the Ekman number. So the Ekman number here, think of it as a small number because the effect of viscosity relative to the rotation, and so it's a small number. Whereas this one, you can think of it as a big number. So this is big, this is small. All right, but yet all of these three, and this is of order 1 because we have measured everything in units of the rotation, and these three terms have to balance. And when they balance, the resulting thing is called a back equilibrium. So you have to pretend this is written in Hebrew and just read it that way around. Okay. So that can be arranged because you got gradients and you got all sorts of things. And so you can muck around, take the curl of this equation and look at its vertical component, take the curl of that equation and take the vertical component, mess around with it. And after a while, you will conclude this horizontal scale, this size of the horizontal columns scales like a typical depth of the layer times the Ekman number to the 1/3 power. So this is what is required so that all these terms are comparable. So basically, if you remember, Ekman number is a small number. So if you keep decreasing it, everything gets smaller. And here's an example of simulations that were done jointly with David. These are in Cartesian geometry, not spherical geometry, but they give you the idea. So this is a plan form. So what you're seeing is these columns getting smaller and smaller as you decrease the Ekman number. Okay. All right. Well, where is the dot? So we have this columnar convection. Now we put in a small seed field and we see what happens. And of course, you have to bring in the induction equation, which has yet another dimensionless number, the magnetic Reynolds number, which requires a characteristic velocity. So that's the convective velocity, which is, if you remember, it takes about 100 years for this thing to go the depth of the layer. Oops, sorry. And then, we have the magnetic diffusivity of the material. That is, people measure it and they don't know it exactly, but let's say they know it within a factor of 2. And then there is this L, what is L? And the argument is that if you're in that configuration, the columnar configuration, this L here is LH, which is the depth of the layer times the Ekman number to the 1/3 power. Okay. And the other thing that is useful to know is that there isn't a universal critical magnetic Reynolds number for dynamos to work. It depends on everything geometry, this, that, the other. But in general, think that it's a number of order 100. So, some number thereof. It could be as small as nothing, and it could be as big as 1,000. But 100 is not an unreasonable number to pick for a geometry like the Earth. And so the idea is that if your convection exceeds, as a Reynolds number that exceeds this critical number here, then any small perturbation, magnetic perturbation, will grow, and if not, they will decay and die. So if you put all the numbers for the liquid core and you use L0, so the thickness of the outer core, you're going to find that the magnetic Reynolds number is of order 10 to the 3, is of order 1,000, which is plenty to drive a dynamo. And so everybody's happy, and you think, great. However, it's not the thickness of the layer, it's the thickness of these columns that count. And if you put in the Ekman number for the Earth, which is 10 to the minus 15, even after you've taken a cube root of that thing, you still got a factor of 10 to the 5 to deal with. And so the effective magnetic Reynolds number, the one that really counts for driving the dynamo, is 10 to the minus 2, which is, 4 to 5 orders of magnitude less than what you need for the dynamo to operate. So the conclusion you would come to is that if the Earth was in the columnar convection state, it could not amplify the field to save its life. And so the Earth would not get magnetized once the Earth is in that particular configuration. It's convecting, it's doing all the thing, it's transporting, the heat and blah, blah, blah. It just cannot amplify the magnetic field. And that's that, because Rm of 10 to the minus 2 is way too small. These columns are 10 meters across. They're way too small. Okay, so the Earth definitely has a magnetic field. So why is that argument not right? And the idea is that, okay, let's go back to where we were and assume that we do have a magnetic field. So we say, okay, we have a magnetic field, and this magnetic field is really strong. So now if I go back to my momentum balance equation with no inertia, I have this extra term, the J cross B. Now I can say, okay, instead of trying to balance everything with this, Ekman term that it's, my principal headache because E is really tiny. And so this term here is the one that buggers everything up and makes everything too small. Now I can hope that I can find another balance where the magnetic forces balance everything else, and I don't have to worry about viscosity. So if that were possible, again, so let's read it in Hebrew for a second, you would have this other type of balance called Mach, where it's magnetic, Archimedean, and Coriolis. So it's not unreasonable to assume that such solutions may exist, that they may not, but given the fact that the Earth actually is sitting there, with a magnetic field, makes you believe that probably these solutions do exist, and that the Earth is actually an example of one of these things. And the important thing is that if these solutions exist, and the Earth is one of them, then it doesn't depend on the Ekman number. It's totally independent. And so the only scale that you have is the thickness of the layer. And so whatever structure this convection is going to have, that is going to be a really complicated one for really other reasons, but it will be a large scale object. And the rotational constraints become irrelevant because the magnetic force can instantaneously balance the Coriolis force. And so the relevant quantity that you put in estimating your magnetic Reynolds number become the thickness of the core. And therefore you get back that your effective magnetic Reynolds number, it's independent of the Ekman number, and therefore is a number of order 1,000. And that makes it possible that now a nonlinear dynamo, in other words, a dynamo that needs a big, strong magnetic field to function, becomes possible. Okay. So in the parlance of these things, the conclusion that you come to is that you can maintain a magnetic field fine. It's just you can't generate it. So you cannot, you have to have it in the first place. And that is the signature of a subcritical dynamo. Okay, so I would like to very rapidly, because I'm sure all of you are very familiar with bifurcation diagrams and all of those things. So I basically have collected everything here, everything that I've said on this diagram here. And so the things that we're interested in is, okay, so the horizontal axis, you can think of this order parameter, let's say it's the Rayleigh number. So you move to the right, you increase the vigor of the convection because you're increasing the convective driving. And so way, way, way to the left in this diagram, there is the critical number for the onset of convection. That's way to the left. Way to the right, sorry, you're driving everything so hard that even the rotation becomes irrelevant. So inertia comes back and all of those things. But we're in the middle, and so we're rotating. We're rotating. The convection is vigorous, but things are such that if you're on the horizontal axis, there is no magnetic field. The dynamo cannot operate. So any perturbation, will just kind of decay to zero. And then when you go above RC, some critical Rayleigh number for which the convection, given its magnetic diffusivity, is sufficiently vigorous, you have this branch of solutions that can amplify a field. But the argument is that the Earth is not in this configuration. And so down here, everything is columnar convection that we said, yeah, but for the case of the Earth is not to the right of RC, it's to the left. And so the other possibility is that you have this finite amplitude branch, which is this Mach branch. And so all along this branch, you have a lot of magnetic field. The problem is that if you go to the left of R min, then there's no finite amplitude solution and any perturbation decays to zero. And the argument that I would like to give, or that I hope of given, is that the position of the Earth relative to this RC is like basically 4 orders of magnitude in magnetic Reynolds number. So the Earth, if I were to put it anywhere on this diagram, is pretty close to just falling off the edge and nowhere near RC. So this diagram is actually quite wrong. It should be a lot more elongated to the left. And so the conclusion is that the present Earth is very subcritical. It's not a little bit subcritical. It's like very, very subcritical. There's nothing you can do to the convection to recover, but it's very good at maintaining the current field, but it cannot restart it. So you cannot hope to magnetize the Earth sometimes in the last, let's say, 3.5 billion years, because 3.5 billion years ago, the Earth-Moon system looked a lot like it does now. And if we weren't magnetized then, there's no way to recover. And so, basically this brings us to the end of my talk, and thank God for that. So what has this got to do with the price of fish? Is that, you have to magnetize the Earth either at the impact or immediately after the impact, or you have the Earth pre-magnetized before the impact, and then you have to have an impact that doesn't unmagnetize the Earth. Because if you magnetize the Earth at the impact, then unless you can come up with some clever way to remagnetize it immediately in the aftermath of the Earth, then you're stuck. You have no magnetic field, and you can't recover. So you can think of these two scenarios. If you were strongly magnetized at the impact better not destroy the magnetization. So you shouldn't screw around with the core too much. And if the Earth was not strongly magnetized, or the impact just wiped it out, then the immediate aftermath better work as a dynamo to remagnetize the Earth to this very strong state. But it cannot be a kind of convectively driven dynamo. You need a radically different type of dynamo than the one you can think of, because we know that if you put unmagnetized convection in there, it's going to be these columnar things that won't work. And so let me conclude. And basically what I said, how did it become, strongly magnetized? So if you think, okay, we go with the scenario that the proto-Earth was magnetized and we didn't destroy the core, then you still have to figure out how this thing got magnetized when it was formed. And so that puts this constraint on the actual formation of the proto-Earth. And so you have these scenarios where you accrete pebbles. So there's pebble accretion, or there's stochastic accretion where you get pelted by bigger objects and so forth and so on. But no matter how you do it, you have to end up with a proto-Earth that is magnetized. So you could say, okay, you dragged in the magnetic field from the interstellar medium, or the other possibility is the way that you formed the proto-Earth from accretion or pebble accretion was very, very efficient at accreting mass, but not at accreting angular momentum. So you didn't have an Earth that was rotating at 24 times a day, sorry, 20 once every 24 hours. And so it was a slow rotator. So it had the Ekman number wasn't that small. And so it could become a magnet. And then, you know, the impact comes along, but doesn't completely wipe out the core, but spins up the Earth. So that's definitely a possibility. But that constrains the protodisk, because, you know, if you look at the models of how you accrete angular momentum as opposed to mass, they're actually determined by the sort of various gradients in the protodisk. So if you go that way, it puts constraints on what the protodisk looked like, you know, the planetary disk that formed the proto-Earth. On the other hand, if you say, no, it was a magnetized, I have no constraints on the formation of the Earth, but, you know, it got magnetized by the impact itself, then, okay, then jolly good, but someone has to come up with an impact dynamo, whatever it may look like. Or you have to sort of say, okay, maybe the impact itself wasn't the thing, but we ended up with a very rapidly rotating Earth, like, you know, the hit and run possibility, or maybe the synestia scenario. And then you say, okay, so it was the immediate aftermath when Earth was losing angular momentum like crazy through, for instance, these things called, you know, eviction resonances or some other resonance. And somehow these resonances, this angular momentum loss, caused a lot of instabilities that drove a dynamo. Or maybe there were these tidally driven instability, like wobble dynamos, that people have looked at, but they think that they won't work because the Ekman number is too small. But so the conclusion of all of this talk is that the fun and potentially promising thing to do is to include, you know, MHD and dynamo considerations into these models of Earth formation, which of course is a lot of work. You basically have to take these codes and whatever and put MHD in them. But on the other hand, you could say putting MHD in a code is a lot cheaper than going back to the moon and digging and getting a lot more rocks and whatever, trying to figure out what happened. So, you know, so that is the message that I would like to leave you with, that this peculiar property of the geodynamo that is so unbelievably subcritical, actually, it is a constraint. It's a very, very, very powerful constraint. And once incorporated into these models, I am sure, you know, if someone will do it, will eliminate a lot of possibilities. And so, you know, we may turn this so-called bad news from Eric into a good news that, you know, we may actually figure out, you know, in more detail exactly how the moon was formed. Okay, thank you so much for listening.
Thank you so much, Fausto. Very nice talk. So congratulations. And do you have other questions? If you have so, please raise your hands. So, well, Pat is first, then Stefan.
So Fausto, very interesting. Now, what is the story in this? You know, there are people, many of them, fortunately not me, who instead of playing with models and computation and other such things, they run around studying rocks, right? And the question is that, I mean, I've heard, you know, for example, I've heard talks on the protosolar nebula and all that, pointing at various magnetic field remnants in meteorites as, you know, claimed as evidence of magnetic processes and the magnetorotational and all that stuff. Fine, but what is the story on basically on magnetization and what might be the remnants of the Great Collision? And how does that illuminate the story? I mean, there must be, I would think there would be the beginnings of a trail there. And what is it?
Yeah, so, yeah, thanks. Okay, so two slightly different answers. So there are two questions in there, and so I'll give two answers. Like one of them is, for instance, you could say, if you look at asteroids in the solar system, some are magnetized and some are not. And so, okay, how do people explain that some of these asteroids are magnetized or some are not? And most of the papers about, I mean, if you look at them, they basically look at energetics. They say, you know, was this thing hot enough, and has it been long enough to convect enough to, you know, to drive a dynamo, and, you know, that kind of stuff. So, you know, they look at how much energy there was and how much of it could be transformed into magnetic energy, and then, you know, how long would it take this big lump of rock to cool and then stop being magnetized, and then, you know, would the magnetization remain or decay? The trouble,
I mean, isn't that sort of a lost cause? Because
it is a lost cause.
you and your esteemed colleague, I believe, had a paper you wanted to entitle "Size Matters," right?
Yes,
you're not going to make it on a small one.
Exactly, but the argument that David and I would make, I hope David will not contradict me, is that the energetics is all very good, but I can tell, you know, suppose you could have two identical asteroids that are exactly the same energetics in terms of temperature gradients, compositional gradients, everything, but one is spinning like crazy and the other one is not spinning. Then the one that's spinning like crazy won't even be convecting, because, you know, it's, you know, if you spin it fast enough, this thing won't convect, or will convect on such tiny column, it will not get magnetized. So it seems to us that in order, if you want to populate the populate, you know, who's magnetic and who's not in the solar system, you need not just you know, how many of these planets were. You don't just need the energetic. You need some distribution of rotation parameters. So you figure what determines, you know, the magnetization within the same family of energetics. It depends on the distribution of who's spinning like crazy and who isn't, which of course depends on the mechanisms that you use to form these things. And so I think, you know, that approach, it's a valid and a sensible one, but it has to be modified to take into account rotation. You have to know something about the rotation of these objects. Otherwise, I would say you can't really say an awful lot about them, because, you know, two identical ones can do either one. In terms of, you know, of magnetization of the remnants of the explosion, yeah, I mean, that is a very good question that I would say it has to be answered within the framework of running these impact simulations. I can see that if you have a very, you know, you have a magnetized proto-Earth and you go for the synestia things where you vaporize the hell out of everything, you know, now you have this big clouds of everything mixed in that probably is not just an iron core, this is everything, you know, so who knows what the magnetic Reynolds number of vaporized rock is, but you would say probably not an awful lot. And so I would say I would not put too much money on this synestia unless, you know, the process of recondensation and you know, reforming the core and everything can get you this magnetic field. But even if it was magnetized before, with an impact that is as disruptive as that, you probably just kind of scatter everything to the four winds. But maybe not. But it's doable. It's, you know, you just have to put in the MHD. so that's the thing. And, you know, it may be that when you put in the MHD, there's no way to make one of those things work. I hope this answered the question.
Sort of. Thank you.
Stefan, you were next.
Thank you. That was great. Maybe this is kind of the same question, different form, but what about the magnetic field of the moon? I gather it's gone, but there was one. Is there the rocks that came back?
Yes, there was. And again, sort of the issue is that, you know, how fast was the moon rotating? so you could magnetize the moon if you knew, you know, how fast was rotating, you know, then, you know, when it was liquid and everything, it was probably convecting, and depending on its rotation rate, you could have, you know, driven, you know, so maybe the Ekman number for the moon wasn't that small. And so, you know, that then you could drive a perfectly sensible supercritical dynamo. And the other possibility for the moon, as far as my understanding is concerned, is that the Ekman number was not that small. That this other type of dynamos called wobble dynamos that are driven by tidal effect may have worked, and people have looked into that, and there is a possibility that you could magnetize the moon with a wobble type dynamo, but the same argument suggests that you would not be able to do it for the Earth. The Earth is too big, and the Ekman number was too small, and it would not work for that. But the Earth, sorry, the moon, you could just have done it by maybe, if the Earth rotation, if the moon's rotation wasn't crazy, you could have done it by convection. I mean, admittedly, the moon is much smaller, so the Reynolds number was much smaller. So who knows? But you have to sort of run the numbers and see what comes out. But you would need to know, if you're going the convection avenue, you need to know something about the spin of the moon at the post impact. I mean, right now it's tidally locked, so you have to figure out what it was right after the impact and put in the numbers.
Okay.
But in Mars is the same. Mars was magnetized and then it wasn't. So obviously Mars, it's done what the Earth is going to do in a little while. It's going to fall off that elbow. It must have had a convective core. It must have been magnetized, and somehow it's smaller. It's a little smaller than the Earth, and so the Reynolds number, magnetic. Okay, the Rayleigh number would have been smaller, and it probably fell off the Mach branch earlier, and now it doesn't seem to have an active magnetism.
Okay, then Xavier, Yannick, and then I'll squeeze in. Xavier?
Hello, Fausto. Very good talk.
Hey, how are you?
Fine, thank you. I was wondering whether there is or not experimental evidence for proving that the J-cross-B force is indeed much bigger than the viscous force, or more generally that the field or the force has the right structure to satisfy the force balance equation.
Oh, yeah. So I would say, in terms of the parlance of dynamo theory, most people would argue that the Earth these days is sitting on the strong field branch, is somewhere around here, is not sitting down here, and furthermore, most people would argue that if that is the case, this branch here is one of these things that people call a Taylor state, these Taylor solutions that has to satisfy this Taylor constraint. And the numbers, yeah. So in some sense, the Earth's magnetic field is definitely strong enough that would put it up here, not down here. So that I think that works out. I mean, if they have to extrapolate and everything, but I think the general belief is that the Earth is in Mach equilibrium, and it is in one of these Taylor states. And the problem is that it's very difficult to push numerical simulation of the geodynamo to Ekman numbers of 10 to the minus 5. Sorry, 10 to the minus 15. So the best that the experts can do at the moment is 10 to the minus 7, maybe 10 to the minus 8. And so you're still many orders of magnitude away from where you want to be. And so inertia is still strong. You still have, you're not in this completely inertialess regime that would give you this Mach solutions. But the biggest, the fanciest simulation seemed to indicate that even though you're still many orders of magnitude away from 10 to the minus 15, you're beginning to enter that regime, that you may not need to go 8 orders of magnitude to 10 to the minus 15. You may actually get into the right regime, maybe a 10 to the minus 8 or something like that. And there is evidence that these big calculations have solutions that don't seem to depend on the Ekman number. So they keep reducing the Ekman number, and they argue that they're getting into the regimes in which the solution doesn't depend on the Ekman number anymore. And so that would be an indication of this, Mach equilibrium. but these are heroic things. I mean, they're heroic calculations that take forever, and they're getting there, but it's going to take years to get there. Yeah.
Many thanks.
Okay, Yannick now.
Yes, as advertised by Guillaume, it was a very entertaining talk indeed. So thanks a lot. My question was related to the large, not large scale, but the large magnitude magnetic field that you need to explain the position of the Earth in this diagram nowadays. So whatever the origin of the large B field of the Earth, either during or before the impact, I was wondering whether one can easily explain the fact that it is still present nowadays, although its generation source or mechanism has gone.
Well, you mean it's a remnant? It's like so there's no regeneration. I mean, if the question is, can you have that the field stays there with no dynamo actually working? It's hard, I would say, because the magnetic Reynolds number is only 1,000. So, if you take something like the sun, the sun is this ridiculously large magnetic Reynolds number. So you don't need a dynamo to explain the magnetic field of the sun, because even if it were a relic field, it will last the age of the main sequence lifetime of the sun. But the Earth, with a magnetic Reynolds number of at most 1,000, this thing would have decayed a long time ago. So basically, over 1,000 revolutions, you have decayed the field, and also it's hard to explain how you would reverse the polarity every 100,000 years. So I don't know. I would say you desperately need a dynamo to keep this thing going. And yeah. So yeah.
Okay. Well, I have two questions, so I'll squeeze in one now. You alluded to it when you answered to Xavier, I guess. And since Nathanael Schiffer is in the audience, he probably will comment. But there seems to be indications that when you go to those heroic computations, actually the length scale seems to saturate, not be dependent anymore on viscosity. And they get to some typical convective length scales of not of the order of tens of meters, but tens of kilometers. So if you have that, and now you put in a magnetic field, what would be your feeling if this single scale hydro to which you add induction could be a good large scale dynamo?
Yeah, yeah, that's a very good question, and the people that do these calculations are much better than I at answering. But my understanding is that a lot of these calculations are kind of expensive and heroic and hard to do. And so more often than not, my understanding is that they're not. You don't start from an unmagnetized state. You start from someone else's calculation that is already, magnetized. And I don't know if someone has actually done the initial value problem starting from an unmagnetized, Earth. Because if it's unmagnetized, it is very hard to see how you would get out of being in vac balance. I mean, if you have no inertia and no magnetic field, then it's inescapable. Your horizontal scale scales as the Ekman number to the -1/3. You only got 3 terms, and you have to balance them somehow. So the issue is that a lot of the calculations that I know about have been started from some previous calculation that started from some previous calculations, a lower, higher Ekman number, and they basically decrease the Ekman number by starting from the previous calculations, and all of these previous calculations are already magnetized. And the question is, I don't know if anyone has really taken, an unmagnetized convection in a sphere, an Ekman number of 10 to the minus 7 or 8, and run it and seen if it can self-magnetize. I'm not sure to what extent that has been done. Maybe somebody knows and can tell me that, yeah, they did it and it worked. But
I guess, well, I guess Nathanael wants to comment, but before I give you the floor, I guess my question was a little bit different, because Nathanael is probably going to say something. But if you were to agree that a pure hydro case gives you a convective length scale of, let's say, tens of kilometers, and now you put an induction in, so you start from pure hydro and you put induction, would the induction mess up that length scale, or would you feel that it would give you a large scale dynamo that would function well?
So if instead of meters as kilometers, you basically you made this thing, your length scale is if you have 10 kilometers as opposed to having 10 meters, your magnetic Reynolds number has just gone up by a factor of 1,000. And so you went from 10 to the minus 2, to 10. And that may be enough to do it. I mean, it may work. The problem that is that why would people believe that it would be 10 kilometers with no magnetic fields? I mean, the Ekman number is 10 to the minus 15. I mean, if either you say, no, the Earth is not a 10 to the minus 15, or if you accept that it's a 10 to the minus 15 and it's in vac balance, then whatever length scale you have for this horizontal scale has to be, 5 orders of magnitude less than the vertical scale. And that is very, I mean, I don't know how you're going to get a factor of 1,000 out of that. That's the problem. But you're absolutely right. If you could have hydrodynamic convection with a scale that is 1,000 times bigger, then the corresponding magnetic Reynolds number would be 1,000 times bigger, and then you have a chance. You have a magnetic Reynolds number of 10, and with some luck, that thing could be on this branch and get big enough to jump to that branch, and just kind of go that way. But it has to be, it all hinges on the horizontal scale being 1,000 times bigger than one expects.
Okay, I guess Nathanael probably wants to comment. So, sorry, Fausto, are you?
Yeah, no, I'm done.
Okay, so Nathanael, you wanted to comment?
Hello, can you hear me?
Oh yeah.
Can you? So yes, hello, I'm Nathanael Schaeffer. So maybe for the 10-kilometer length scale, indeed, if you drop the viscosity before, because Ekman number is very, very small, indeed smaller than the Rossby number, then you get some Rhine scale instead for the length scale of your flow, which is about 10 kilometers. So this is one possibility. And we have simulations, so non-magnetized simulations that tend to support that. And so maybe the other comment was about the subcritical. No, what was the yes? Can you start a dynamo from scratch? From magnetic noise instead of from someone else's calculation. So indeed, this is what we do. We start from some other magnetic field, so we don't start from zero magnetic field when we do these calculations.
No, zero wouldn't get you there.
Yeah, sure. No, noise. I mean, small noise. Yes, we don't start from a small noise. We start from finite amplitude solutions. And to answer your question, no, I don't think anybody has done it for very small Ekman numbers to start from small random noise. So this is one part of the answer. The other part is when we do it for larger Ekman numbers, we can start from noise. from small scale noise. So
yeah.
So you have yes. So basically, you start from high Ekman numbers solutions which are supercritical, and then you go to lower Ekman numbers. Maybe you don't know if they are supercritical or not, but I didn't. This is something I didn't get in your talk, so maybe I can ask the question. What is exactly the argument of saying that the Earth is so subcritical, as you say? I failed to understand that.
Oh, it's a combination of, I mean, it's not a very sophisticated argument. It's a combination of the fact that if the Ekman number is very small, then you know, you have no inertia. You know, the horizontal, basically the momentum equation is this one. This is your momentum equation. You don't have inertia terms, but the inertia terms become irrelevant in this framework as you decrease the Ekman number, and you have to really decrease it a lot. You have to have very, very small Ekman number before the inertia terms pull out. But once they become irrelevant, then it's very difficult to figure out how you can have any solution that doesn't satisfy these, you know, back balance, because, you know, okay, given the fact that this term here is not important, that's all you have. And you know, this is what's driving everything, and these two are not aligned with each other. So you need these three things to be of the same order, and whatever makes them of the same order implies that the gradients have to scale in this funny way.
Okay.
This is not true if you have inertia. I mean, if you have an inertia term here, that this is not true. So, yeah. At small Ekman number, but not incredibly small, you still have inertia that can do things for you. But at very, very small Ekman numbers, it's very difficult to escape from this relationship, I would say. I mean, especially by a factor of 1,000. You know, maybe some geometrical factors to do with spheres as opposed to, but 1,000 is a lot.
So yeah. Yes, so
in
my view, I would drop the viscosity before dropping the inertia, because Ekman numbers here is 10 to minus 15, and the Rossby number that you use to drop the inertia is only 10 to minus 6 or 10 to minus 5. So
yeah, but I mean, yeah, but if you, that is fair enough. So, but yes. If you stick back inertia and you know, I can solve the equation. No, I can't, because, you know, if you put back inertia, then this equation here becomes so stiff that, as you say, you know, at the Rossby number of 10 to the minus 6, your epicyclic frequency is so incredibly high that you're trying to, your time steps becomes negligible. But if one were to do it, yeah, this term here would still be, you know, 10 to the minus 6 times compared to this thing. I mean, I think you can put it back, but basically you're getting this wrong to 1 part in 10 to the 6. And so it's still hard to see how you're going to get out of this mess. And it's still, you know, it's still a system that very, very rapidly equilibrates with the Coriolis force and any change in forces. So it's a funny, you know, when this thing gets small, it's odd, because it's one of these systems where you know, the velocity depends on the forces, not the acceleration. But again, that is not true only in 1 part in 10 to the 6. So it's still tiny. So I don't know. I mean,
yes. So this is where we have a different approach, actually. So
yeah. But you're absolutely right. If you have inertia, you can find different you know, different balances that are not vac. But if inertia, if this is true, or true to, you know, 1 part in 10 to the whatever, then that statement is true to the 1 part in 10 to the whatever. And so I guess you know, the answer to your question, or the resolution of that issue is like, you know, how important is inertia at the Ekman numbers that you're working at? And,
yes, exactly.
Yeah. Yeah. So here it's all based on the assumption that inertia is irrelevant.
Yes. Okay.
And you have a turnover time of 100 years and a rotation time of 24. So no, not 24 years, 24 hours. So inertia is probably not very important in the Earth core. But anyway, thanks for it's. I mean, it's a very interesting question, and it has to do with how big is inertia.
Yes. Thank you for your answer.
Bindesh, now you have a question.
Yes, thanks. It's a very interesting talk, Fausto. Thanks for sharing. I am a little bit interested more on the astro side. So since we have worked extensively on solar dynamo problem, could you also comment a bit on whether the solar dynamo is subcritical or supercritical?
Oh yeah, thanks. No, I mean, I don't I don't think anybody knows what the solar dynamo looks like or does, but in the sun and the stars, you're dealing with ionized gases. So these things are very good electrical conductors. So whatever you may argue or whatever you may do, your magnetic Reynolds numbers are huge, and so there never is any question of this thing not being a dynamo. You may have no clue what kind of dynamo it is, but as I was saying, the magnetic Reynolds number for most astrophysical object made of ionized plasma, they're so huge that you don't even need a dynamo. Even if you were to stick in a magnetic field, when this thing was formed, where the sun was formed, it still would be there now. The decay time is so enormous. It's like it's in the billions of years. It's comparable to the main sequence lifetime of the sun. The reason why everybody wants to stick a dynamo in the sun is because, of course, you want to explain, solar activity. You want, the solar cycle. You want active regions to bubble up everywhere and go away and reverse the polarity and this, that, the other. But in theory, you don't need it. I mean, they're so huge that you can just magnetize everything at some early epoch and just leave it to that. So I don't think that you could, even if you rotated the sun at some crazy speed that it was close to the Eddington rotation rate, it would still be subcritical. Yeah, I don't think. Yeah, you blow up the sun before you kill the convection or you go to small magnetic Reynolds number. So yeah, stars operate in a completely different regime.
Okay, Nick, you have a question?
Yeah, hey Fausto. Full disclosure,
Yo.
I have heard talks by the other author.
Eric, right?
By Eric, also by David, of course. Mach balance and back balance these are all asymptotic limits, but we're never quite in the asymptotic. Is this some intermediate state, which is not VAC or Mach, but MVAC?
Yeah. So yeah, God, I mean, So yes, so David and I have, yes, I think most of the simulations are not in these asymptotic limits. Most of the simulations are somewhere in between. I mean, okay, David and I have different thingies because we just throw away the inertia in the first place, and so we just do away with it. So there is no inertia from the word go, and so that is gone. If you solve the full equations, as I say, at a magnetic Reynolds number, at an Ekman number of 10⁻⁷, you still have some inertia left. So you're not quite in these regimes. There's a review by Bruce Buffett that basically grabs all of the possible simulation that anyone has ever done and analyzes them to figure out whether they're in VAC regimes or Mach regimes. And the conclusion is that most of them are all in these VAC regimes still, but they're slowly creeping into getting, so we're at the threshold that if we're optimistic, the next generation may be in the Mach regime. But we're just getting there. The inertia is still big. You still have inertia. I mean, they do it by running the simulation and literally calculating the magnitude of each term. And, so inertia is small, but it's not that small. It's not 10⁻⁵ or 6 times smaller than, a Coriolis force. So we're not there yet. So most of the solutions are not quite Taylor states. or pure Mach, equilibria or whatever.
But do they even look like they're tending towards Taylor states? I had this feeling that Taylor states have been very elusive, right?
Yeah, God, yeah, no, they're not, absolutely not Taylor states yet, not at all. So, there's this Taylorization parameter, and that people can compute, and it goes between plus and minus 1, and if you were in a Taylor state, it should be 1 or minus 1. But if you apply it to simulations, you work it out. And not everybody does that. So not, there are lots of simulations that do not tell you what their, Taylorization number is. So I don't know. But by and large, you find that these Taylor numbers are kind of all over the place. This, Taylorization parameter is all over, is everywhere between, it looks like salt and pepper. Someplace, it's close to being Taylorized. Some places completely not close to Taylorized. It varies on tiny, teeny weeny little scales. And we one suggestion from Paul Roberts and was that maybe depends on scale, so you're Taylorized on large scales, but you're not Taylorized on little scales. But then you can argue, what does that mean? Of course, viscosity acts on small scale. So what does it mean to only be Taylorized at large scales? At large scales, you've killed viscosity anyway. So, but I think everybody would agree that if these heroic calculations are getting into these asymptotic regimes, they're just beginning to do so now. In other words, they keep decreasing the Ekman number and things change, and then they decrease it a little bit more and things don't seem to change. And so they interpret it by saying, okay, we are entering into the regimes where the solution is Ekman number independent. But we don't have orders of magnitude of, Ekman number variation where nothing happens. They're just getting in there. Yeah.
Okay. Well, I don't see any other questions, so if I may, I'll put in another one. Since the determination of the dynamo is obviously something quite important, especially for the Earth. And there was a dynamo on the Moon for, let's say, 1 billion years, it seems. Can you say something, given the fact that the composition is so very close and everything? Can you say something studying the Moon about how it would end up for the Earth then? Or the Moon is just too different, too small, it has other means to develop a magnetic field that basically extrapolating to the Earth is so very difficult.
Yeah, no, yeah, thanks. That's a very good question. I mean, as I say, the sensible thing to do eventually, if someone has the resources to do it, would be to put MHD and just do the lot, formation of Earth, Moon, and see, who gets magnetized, who doesn't, and all of that. But one possibility that the Moon is somewhat different from the Earth is that the Moon, it's small enough and its Ekman number is large enough that it could be subject to these instabilities called wobble instabilities that have to do with tidal effects that that could be dynamos. So a long time ago, there were these papers by Willem Malkus that he was advocating this type of dynamo. So these are tidally driven, and the tidal effect of the Earth on the Moon is a heck of a lot bigger than the one of the Moon on the Earth. And so, people have argued that and the Ekman numbers are different. So one way of magnetizing the Moon is to invoke these wobble dynamos, and they could do it to the Moon, but the general feeling is that they couldn't do it to the Earth. These wobble dynamos wouldn't work on the Earth because it's, as you say, it's bigger and the tidal effects are much weaker and so forth and so on. And so they wouldn't be able to drive instability strong enough in the liquid core to do it for you, but they could on the Moon. So in that sense, the moon has other avenues that are precluded to the Earth for getting itself magnetized.
Yeah. The moon is actually a bit of a mysterious object, because if you measure the magnetization of rocks, it's actually much more magnetized than they think is possible by an earlier core dynamo. If you take all of the energy of the moon, put it into a core dynamo, say it got, so say it was an equipartition energy, created that sort of dynamo field, and then said, what would that do to the magnetization of the rocks of the surface? You get more magnetization by measuring the rocks than you would out of that. So the moon is a bit of a mystery, and there's all these theories about basal magma oceans and blah, 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 which, I mean, so nobody understands how the moon got to be the way it is right now. So it's very hard to then use that to sort of solve Fausto's problem.
Yeah, but it probably gives you a lower bound, because you say that it has other avenues to sustain a magnetic field. So because it has terminated in 1 billion years, it probably gives you an upper bound of what will happen on Earth or Mars or whatever. Is that a good reasoning, or no? It's just rubbish because of those other avenues possible.
Sorry, are you asking me or are you asking Nick?
No, you, I guess, or
no, you're asking Nick, because that's his
okay, no,
comment.
that's fine.
He brought it up.
Okay, I saw that. Well, David, you have a comment on that, or Pat first?
Yeah, I have a sort of comment on that. I mean, I think you're asking is, I know, Pat, I've jumped in front of you, but that was blame Guillaume.
Typical British, doesn't know how to queue up properly.
The French. The French is responsible. I'm sorry.
The French just had a better idea of, importance. That was all. But I guess, Guillaume, you're asking if the moon has dropped off the cliff in Fausto's bifurcation diagram, right?
Yep.
And that if we knew how the moon started, and we knew how quickly we were progressing down,
exactly,
and we knew where the cliff was,
yeah,
and we
how much momentum
knew when the moon fell off the cliff. Maybe we do know when the moon fell off the cliff. Then that is true. Then all those things being equal, we could say something about the Earth's field, I think. But I don't think we do know where the cliff is.
Okay. Okay.
Well, certainly no one at this computer.
But yeah, I mean, maybe there are these kind of energetic arguments about, but they're difficult,
Yeah. I mean, the other one is Mars. Mars must have done the same thing. I mean, it was magnetized and it's not magnetized anymore. So Mars, I think, definitely fell off the cliff.
That was my question. I mean, since Guillaume started taking us on a tour of the solar system, could you briefly summarize the stories of Mars and Venus and what we think we know about them?
Oh, I am so not the person to do that. I mean, I wish.
Well, maybe like one of the assembled experts,
Yeah, I mean, like someone like Chris Jones would do an infinitely better job than me. But Mars, my understanding is Mars is very similar because it has a similar rotation rate. It's not that much smaller than the Earth.
Right.
Mars is a definite candidate for being, a precursor of the Earth, and everything that has happened to Mars eventually is going to happen to the Earth once it just happened sooner because it's smaller, and so it had a smaller core, it solidified it all, and once you're totally solidified, there's nothing to drive your convection, the dynamo dies and you're dead, and that's that. And so I would say that Mars, because of the rotation rates and the size and everything, is like a little Earth, and so its Rayleigh number is a little smaller, but it's all the same thing. Venus, as far as I understand, is a completely crazy thing. I mean, it doesn't rotate. I have no idea what's going on with Venus. If it has a magnetic field, it's a very, very weak one, as far as I understand. So Venus is radically different from from either the Earth or Mars. But I think Mars is just like a preview of what's going to happen to the Earth. So at some point, the core will be all solid or pretty much all solid, and then the Earth, and then it fell off. It will fall off the cliff. And maybe, I'm sorry.
Well,
I'm
when Mars fell off the cliff.
I have no idea, but maybe we actually no. Yeah, sorry. So I read a paper recently. Someone was claiming that that they knew. I can't remember what the argument was, but somebody's definitely claiming that they can say when it fell off the cliff. How long ago, and I guess with all these little machines running around the surface of Mars, that will know more about it as we collect more bits and bobs of Mars. I mean, the Earth, there are these rocks that are 4 billion years old that are magnetized. So the Earth, that it was magnetized all along, or pretty much all along.
But these people,
Mars. Sorry, go ahead, Patrick.
These people who go around studying planets, how many of the surveyed planets have been able to have a or what fraction, say, have a magnetosphere associated with them? Because that would be obviously one long-range indicator of the fraction that did or did not fall off the cliff.
Yeah. But the other thing you have to bear in mind that when you start dealing with with gas giants like Jupiter or Saturn or those guys, of course their hydrodynamics is completely different because they rotate like crazy, but then again they're made of metallic hydrogens. So God knows what the convection looks like on Jupiter, but just looking at it, you think, no, this is definitely some system where inertia is very important. I mean, this guy's got jets everywhere. So they're in a completely different regime than the Earth's liquid core. And I don't know what the magnetic Reynolds number is for Jupiter, but it's a completely different substance. So I think you have to put the gas giant, the gas giant planets in one basket, the water planets in another one, the rocky ones in another one, and so so Jupiter has a phenomenally active magnetic field, and Saturn has this crazy magnetic field that is so axisymmetric that no one can figure out why it is so terribly axisymmetric. So they're all a little different, but I'm not sure to what extent figuring out what's going on with Jupiter would really help you an awful lot with the Earth.
Has that sort of zoological study been done?
Oh yeah. As I say, I don't know if Chris Jones is online or if he's taking part of this thing, but there are lots of people that can give you very, very good reviews of this subject, and I am definitely not one of those people. But yes, I mean, a lot is known about magnetism of the planets. Yeah. But as I say, I mean, Jupiter is a gas giant. The Earth is a rocky thing. So they're very different. It's like it's like the sun. Knowing everything about the solar dynamo hardly tells you anything about the Earth.
Okay. Well, thank you very much. I don't see any other questions, so I guess we'll stop torturing you. So thank you very much for this really entertaining.
Guys, thank you. You have no idea what a pleasure it was to to be alive again.
Well, and I hope to see you in person
next year.
in a year or something.
Yes, absolutely, guys. Yes. Yeah, go out and have some Pernod, whatever, Moresque. All right. Thanks, everybody.
Okay. Cheers.
Bye-bye.
Thank you very much. Bye.